is important? Why do we need to make an energy mapping in the first place? And I think one important thing is often when we are looking on a production site, then I don't know if you can see my cursor. Can you see my pointer here? Good.
Yes, we can.
Okay. So when you're looking at a production site, that could be the elephant, represented by the elephant here. And there's a lot of people working on this production site. We all have different views on how this production site looks. And this is related to our specific activities at this production site. So first of all, to create a common or mutual understanding of how the production site looks is extremely important in terms of working with energy mapping and also with optimization. Then it is important to connect the energy mapping to processes and process-related conditions, because you can measure how much steam that you're producing on a utility level, but that doesn't tell you anything about how what is the demand from the process, from a process perspective. And this mutual understanding can be done in many ways, and often it's one of the most challenging tasks. And we have, from experience, it has often also been some of the most time-consuming processes. Even though on the first meeting, when you are doing an energy audit where an energy mapping is included, then everybody can agree that we know what this process is about. But when we start digging into the details, there are many different discussions and many different angles to how such process looks like, how it's designed, how it's operated and run. Then, of course, to have such an energy mapping, the energy mapping is the basis for making any decisions. Because when you start developing projects, approaching your team with a project idea, then you should have a common basis for deciding whether a specific project idea is relevant to pursue, or if it should be parked, put on hold. Because one could think that this specific project would save, let's say, 20% of the energy consumption, but when you look into the energy mapping, it only accounts for a few percent. So having some facts and a basis that everybody has agreed on, that this is the right picture, is extremely important, and it saves a lot of time when you're working with developing projects. And of course, it's also important that when you work on the energy mapping, then it reflects the strategy that you're having in the company. Are you optimizing the costs, operation costs, the energy consumption, the carbon footprint? What is the focus? So having that in place is also important. Then I don't know if you are familiar with this onion diagram, and it might be kind of hard to read, but the principle of the onion diagram is that when you're doing any energy optimization, it is important to first focus on the actual energy service. And what is the energy service? Energy service is who requires the energy. So we have a process that needs to be heated from one temperature to another temperature. This is an energy service because this is a service that supports the process directly. The energy service is not combusting gas in a boiler. So let me give you an example. If you have an optimization, then if you are optimizing your energy service, so reducing the demand for the process, then that will save the energy, of course, for the process itself. It will also save, to some extent, the energy for transporting or distributing the energy from the utility system and towards the process, and would also save energy at the utility systems. If we look at it the other way around, so optimizing the utility system first, Then you can optimize the utility system and you will save energy on the utility system. But that will not have any impact on the process or the distribution system. So it's like a one-way. So the point is here, focus on the energy service. This is the most efficient approach. And this is why this energy mapping is so important, because this gives you an insight to what the energy service is. Often when you are looking at such a process, you can pull up a lot of P&IDs, and you have, when you walk around on the processes and the production lines, the process will look something like what we have in the picture, and it's very hard to determine what is actually for what. And so creating this clear picture before starting, breaking out the process in main components, putting them together, and then highlighting all the elements that actually have an effect on the energy consumption, a major effect. So having control of the mass balance throughout the process, and then you can start build up on the energy mapping. So removing all pipes, valves, vessels, whatever that has not directly effect on the energy consumption itself, makes it a lot easier to work with the energy systems. And then, of course, at what level of detail should you build this energy mapping? And we will get back to that when we also show some example of the energy mapping itself. But this is a question that is very hard to answer, because it depends on a lot of things. And I think it's something that is a process. And the first point here is that when you start, you build it on the available data. And then you see how good is your energy mapping? How much can you account for? And then you can decide whether the level of detail should be increased, or whether it should be, or whether it's sufficient for the work that you are doing. So here are some examples. Creating this overview, I have a picture in the next slide where you can see it even better. So making this EPEFD, energy process flow diagram, just creating this overview, how is everything linked, how is energy consumed? And of course, it's also important to have a fairly good idea of where all these different energy consumers are located, sort of on a site level. So having a site layout where these different sort of areas or production zones are highlighted, located. So you have these two illustrations to support the energy mapping. And then you start up with the energy and mass balance. And there's a lot of different ways. This is like a big puzzle when you do this energy mapping. There can be a lot of different approaches on how to retrieve different data. Yeah, this is just an illustration of these different, this is the entire site, circle around in the red dotted line, and then there are specific process area, and you could focus on one process area with the blue area here, or you could narrow down to one specific unit and focus on that. And this is all something that will be treated. But what you can see here is, for example, this is a dairy, and what we see here is that we have some milk coming in up here, and then we can follow the milk flow. At some point we will get some cheese, we will get some whey, and we have some other waste streams associated with this. But we can follow the flow. We can see where do we use steam, where do we use cooling, where do we have a recovery system. And here we have illustrated what kind of supporting system is also present for supporting the process. So here we have a recovery system, here we have some CIP, some cleaning systems, and here we have boilers, we have chillers, and so on. When we start gathering data, we often ask, we need to measure everything in order to get a very precise energy mapping. and so we can account for everything. And I think this is this is a big mistake of when you start out anyway, because you can easily end up drowning in data, spending a lot of time on measuring. And if you're not measuring over a representative period, let's say 1 year, you will measure 1 day, you will have to do a lot of assumptions anyway. So you add a lot of uncertainty into your measurements. So when you go and approach a site and try to collect data, there is, of course, all the measurement that exists on site already. Use them to the extent that you can. But there's a lot of other ways of gathering information. Talk to the operators. They might know a lot about how the process is operated. Maybe they don't have any data that is logged that you can get, but maybe you can find a meter somewhere. Maybe they know by experience some in things. You could maybe look at trends. Could be manual reading. Of course, there's the metering. There's also experience that you as a consultant can bring in to the mapping when you are working on other side. You have experience from similar processes, comparison with similar equipment. You could take a theoretical approach, information from suppliers of the equipment, could be performance tests, process diagrams, site plans, metering plans. So there could be a lot of different ways of getting these information. The most important thing is here that the information that you put into the energy mapping is information that you can account for. So you can say this temperature is maybe based on a energy balance, is based on a manual reading. And then you can say, this is the best figure that I have at the moment. So I choose to use it because I don't have any better information available. Next step could be measuring the temperature with an external measurement device, but wait before you can justify why should we spend additional time on measuring this specific temperature. And one way of justifying is if you can justify that you have located a potential project, or if this contributes significantly to the quality of your energy map. The structure of the tool is, it's an Excel tool, is relatively simple. The most difficult part can just be understanding the methodology and the thoughts behind using the tool. Once that is in place, then the tool is relatively simple to use. It's a spreadsheet consisting of a number of sheets. We have one called administration, one called overall result, one called yearly data, one called mass balance, mass flow balance, process mapping, utility mapping, and supporting system. And of course, this can be modified for the specific production. You could add additional sheets to this file. But this is, when you work with it, this is just, adding in whatever is needed. One sheet that we have not included here is a sheet where you can actually track any changes. So if you go in and make any changes, then you can list that, so you can follow who has been working with and who has been making changes. It could also be stating comments to where the data has been retrieved from. So there's a lot of ways where you can put in maybe some more information that you could use. And just before we go to the energy map, it's also important that when we do this energy map, the first time it's made, it's relatively time consuming to do it. But when you do this energy map and when you develop it for the companies, keep in mind that when the energy map should be updated, it should be as easy and as fast as possible. So try to make the mapping as dynamic as possible. So let it depend on the process and the production as much as possible. and less on fixed value that need to be updated every time. So if you can just change the process values and some yearly data input, then the energy mapping could be updated relatively easy at a certain interval or frequency, and it could go into both the energy audits and other things. Okay, I will leave the floor to my colleague Anders Lund, who will present the energy mapping, and I might also contribute to that part. The floor is yours, Anders.
Thank you, Fridolin. Introduction to the tool. Here are some of the main steps that usually work when you're doing an energy mapping. So often you have to know the site. You have to get a mutual understanding, as Fridolin already said. So everyone agrees on what is the basis of the energy mapping. You have to draw out these ePFDs so you can follow the energy flows as well as the mass flows throughout the system. You can start mapping your utility systems and where your distribution systems are going from and to. You then have to do a mass balance, an energy balance. You can then see the analysis and then get the results on the energy consumption, but I'll get more into this. Here you see another flow chart, kind of stating the workflow of the whole energy mapping part. You will have, in the beginning, you have to define all the goals and the scope of the mapping. So you have to know what you would like to use the energy mapping for. Then you have to go and collect the site data. And then you create an overall overview of the process. And then you map the flow of energy and mass streams. And then you analyze on the data at the end. Yeah, so what should the mapping be used for? Should the mapping include the entire facility or focus on certain areas, depending on what level of detail you have for data? And what given timeline do we have? So can we achieve the data needed? And also this economic evaluations, or is it meant to be focusing on emissions and environmental impact? So is it better to focus on the electrical parts or the thermal parts? So this is a thing that you have to understand from the beginning of the energy mapping process, that it's important to know what should the mapping be used for. So if we go into the methodology, then you need to collect your overall data. So this could be, you see on the figure here on the right, that all the energy data that you purchase. So you have electricity, coal, natural gas, whatever biomass that you might have. And then you have your raw materials. And then you also know the production quantities. And that is shown in the sheet called yearly data. And you can see the Excel sheet right now. Yeah. So this is the sheet where you input all your data. You should only be adjusting all the yellow cells. Then you have the gray cells, which are calculation cells. You also see that you have this is the front sheet. You have a small explanation of each legend or each color, so you can see what they're used for. But this is the main input sheet to the mass flow balance that you will see in the next slides.
One comment, Anders, to the sheet is the idea is that all these information is information that are almost every time available on site, because this is the amount of energy that you purchase, is the amount of raw material that you put in to the production, and is also the output from the production, so all the products that is leaving the process. And these are figures that the companies are keeping track of as a minimum. So these are the figures that we use for the mass balance, and we also use it to compare our energy mapping to what we have actually bought. And then, of course, it's important to be aware of the units. This is kilowatt hours per year. So we are looking at it on a yearly basis. And it's kilowatt hours, or the mass is in ton. So being very strict about using the same units throughout the mapping, otherwise you can get into some different conflicts. Yeah.
Yes, definitely. And maybe it should also be said that it's important that you customize this energy mapping towards your specific site. So not every site is alike, and therefore there should be made minor changes to this mapping so that it fits the best to whatever site is working on it. Yeah, the next phase is to make an overall overview of your processes and the utility. So that could be done by constructing a simple process flow diagram. Here, not taking account into the mass flow or the energy flow, just simply sketching up the production lines in order to get this mutual understanding of how does our factory actually work from our raw materials coming in until the final product coming out at the end. And that will be used in the utility mapping part and also in the mass flow balance that we have as the next thing here. So
maybe Anders, you can open just show the spreadsheet also.
Yeah. So we have the mass flow balance in this sheet called mass flow balance. And here you should sketch the production line.
Anders, could you please zoom in a bit?
Yes, of course.
Yeah,
Is that better?
Yes, yes.
So we have all our raw materials coming in, referring to the yearly data sheet here. And then we have labeled all our streams going through the processes. And then here we will mark whether it uses or consumes energy. Here we have the red one is heating, and then we have electricity for the green one. Then we can follow the mass flow throughout the system. And again, please only edit in the yellow cells, because that's the best way to adjust for the mass flow. So here we have entered a fraction of this incoming mass flow to process C, and that then distributes in stream 3.1 and stream 4. And then you can follow the mass flow all the way from coming in to a final product at the end. And then you have a mass flow check, kind of measuring if you have mapped all your masses, or do you lose any mass throughout the system. Also, perhaps you have some production line that is related, and then you will have a stream going out saying this goes to process line 3 instead, and then you have it. Then it will continue afterwards down here. And also this sheet's important to adjust it to your process. You can have as many process lines as your factory might have. Yeah. And this is then the basis of the process mapping part, the next sheet.
Maybe Anders, just a few comments.
Yeah.
When we look at the mass balance, what I mentioned earlier was that try to make this model as dynamic as possible. And here is an example of where you can see that if you go a bit up in process line 1, we have process A. We have the sum of all the incoming raw material going in, being mixed. We have the sum of that going out in point number 2. Then we add in some additive to process B. So we increase the mass over process B, going out in point 3, entering process C. And here we have a split in process C. And here we say 25% of the incoming flow is split down to point 3.1. And here it says this, that's just a comment for the reader, say this point is actually entering as an input to process line number 2. It could be a waste stream, it could go anywhere, but again, then if this is a fraction of some input, then if you adjust the input and the fraction is constant, then the mass will just adjust accordingly. So this is a way of making the energy mapping as dynamic as possible. You could choose, if you don't have that fraction, 25%, if you don't have that figure, you have some specific measured values instead, then you can make your own fraction based on that. And of course, here it's important to have a discussion with the production side, whether this is a constant or what does it depend on? Does it vary from year to year, or what is the dependency of this? But then here is highlighted in yellow, so this is something that you should investigate every time you update. Is this still the same value? And as Anders said, we have some check, and these check are just to make sure whether we are how good we are accounting for our mass balance. So the mass balance check, as Anders mentioned, is just checking whether all the inputs are equal to all the outputs of the system that we have designed here. And then the not map part actually compares what is coming out of this process line compared to the output that we have stated in the yearly data file. So here we have stated that we have a product output, and we compare to what does our mass balance tell us that we have. And here we can then see, okay, is it okay to have a not map part saying that there's a part here of a 3.7 thousand tons that we can actually not account for. And that can be due to many things. It can be due to the uncertainties of the raw material coming in. It could be to the additives. It could be to the shared factor, or it could be to some other losses that we have not accounted for. And of course, this is again something we need to talk to the company. Is this okay to have this amount of mass that we can actually not relate to? And when we approach the company, and if it's of a certain size, this mass that we cannot account for, then suddenly it will emerge that, okay, it's because we have not included a mass stream going out. And then we can include it, and then we can improve the energy mapping even further. So it's also a help to see if you're actually accounting for everything. And this is why it's so important to use the data and let the data speak for itself, and not try to fit the data so you can account for everything. So, because then you cannot learn from it. Yes.
Yes.
Sorry,
as mentioned earlier, you should use the data you have available. Whether that is, of course, data collection is great. If you think that is representative, that you have a long period of measuring time, and you could also, if you don't have that, have estimates or calculations of the mass flows, and that could also be these mass fractions that is estimated based on your experiences. Yes.
And then maybe just a short comment before because here we are only focusing on the mass. So don't, okay, of course, if it gives you a value and an overview, you can put the energy into these different arrows or lines that we have put in, but here we actually only are addressing the mass. Energy will be addressed in one of the other sheet.
Yes, and that would be the next one here, where you are calculating the energy balances. This is where we consider heating, cooling, electricity, but also the waste heat distributed throughout all of our production lines. So we are doing that in the next sheet, where we have these tables. We have different approaches to quantify our energy consumption. You can perhaps use the calculated mass flow, that is a theoretical based energy consumption. You could also have a KPI for a specific unit that is also based on mass flow. And then you have, if you have measurements, direct logging of your energy consumption, that can be used as well for the energy mapping. So,
Anders?
Yes.
One thing is when you are, I mean, as you can see, the two first sort of approaches were proportional to the mass flow. And the last one was, this is a fixed value that you can type in. But you should consider maybe if you can collate it to the mass flow to build in this dynamic element into the mapping using a measurement. Yeah,
that's correct. Creating an energy mapping that is as dynamic as possible obviously makes it easier to make the energy mapping year after year, because you can just re-enter a new mass flow and then it recalculates all the energy consumptions. So here we have our heating consumption, the cooling consumption, we have our waste heat, and then we have electricity consumption. And these three columns are describing each of the measurements or calculation methods. You then enter again in the yellow cells, you have the temperatures of each process. You note here that you enter the stream numbers, which refers to the mass flow balance over here. So you can follow the energy throughout the mass flow as well. You have to describe the utility system as well, and the inlet temperature and outlet temperature. Then it will summarize the different energy consumptions of the different approaches and the total heat consumption here. In the top of this, you can describe a significant energy user, which is a process or process equipment that uses a vast amount of energy that you can then enter a value. Here it's 15%. So if a certain process uses more than 15%, that is defined as a significant energy user, and you should perhaps follow that regularly and making KPIs, because this is a large energy consumer. For example, you see here in production line 1, we have process B uses 46.6% of the total heat consumption. So if this makes any changes, or it would be a good process to make energy optimizations on, at least. Yeah, but that is defined by the site itself. What percentage should the significant energy user be defined as? Yes. Do you have some comments relating to this sheet?
Yeah, I have. Maybe we can, if you can go one step back to the mass balance.
Yeah.
And if you go down to the example of process line 2, it's just to mention, because we have a term also in this process mapping sheet where we call dry matter. And this is just another way you can see the DM in yellow. Oh, yeah, in yellow here. Yeah, exactly. And this is just another way of saying, because often some of the processes are, the purpose of that is to remove some liquid somehow. So you want to increase the dry matter content throughout such a process. So using this dry matter content as a way of describing your process could be another approach also for the dynamic, because often if you are having a process where you remove water, then the dry matter is relatively fixed if it's the same product that you're producing year after year. So this could be another way of accounting how the mass is distributed throughout the process. And if you go back to, and this bit, the small table below was just an example of looking at the balance. But here we also have the dry matter, as you can see in this column here. And here we actually mostly use it if it's used as to define the specific heat of this product flow. This is the only reason why it's included in this sheet, because sometimes the heat capacity is a function of the dry matter and the temperature to make with a simple correlation. So this is why it's entered here. And you could also, in this case, the specific heat is calculated based on the dry matter and the temperature assumed, but you could also just put in whatever value that you have. If you have better knowledge, this is for, I guess, something that is very water-like. But if you have another product with different heat capacities, then just enter the heat capacities in column K for that part. And if you scroll down a bit to the surplus heat, yeah, this one. This is a element that we have included because it is to get also to map potential waste heat streams are also often quite useful, because you can have discussions on how to reintegrate these waste heat stream into the process, saving primary energy. And the way that we have done it in this is often we have the temperature of the initial temperature of the waste heat stream. So the temperature of the stream, let's say, is wastewater going out at 50 degrees. So we have the 50 degree, and then we need to say in terms of mapping it, to what extent do we think that we can reduce this temperature? And often it's good to have a common sort of temperature reference. So in this case, we have said 20 degrees. So here in our mapping of our waste stream, we assume that we can reduce the temperature from 50 to 20 degrees by applying some cooling methodology, or by integrating so we can actually get this heat in return. So it's just a way of doing it. It could be any, depending on the local condition and what we believe in. Let's say if you were in Denmark, we could reduce this to 10 degrees because the temperature is lower. So often we could go lower, but I mean, it depends on the situation. It could also depend on the media. So let's say now we have product, we have water. In the case of air, it might be different. So we could have 50 degrees going out, and maybe we have 100 degrees going in. So, but this is something that, I mean, the only information that we have is the temperature going out and or going in. We need to set the temperature with the best estimate ourselves. And this is, of course, something that should be adjusted as projects start to develop. And then if we go down to the electricity one, here we have a slightly different approach, because the electricity consumption is a bit harder to sort of make it as a function of the mass flow. In some cases, it can be done. We can make a functional correlation, so we can actually say, how does the electricity consumption for a certain process actually relate to the mass flow. But what we do here is that because we have located all the electricity consumers in our walkthrough, so, and we have noted the effects, we have a fairly good idea, or we will ask anyway, the production, how many operation hours does that unit have? And then we can also say how, I mean, the factor of how it's being utilized, the load factor on this, how big is that? And then we can go actually again then with 3 approaches. We could correlated to the mass flow, we could generate the KPI, or not, so not the mass flow, where we calculate, we know we have the effect times the operation hours times this load factor. That gives us one way of doing it. Then we have a KPI we could use also for generating, and this KPI is based on the mass times the KPI. So here we have a sort of a correlation between the mass and the electricity consumption that we have tried to build in. And again, then try to see if you can make this as dynamic as possible. So if your first approach is a measurement, and could you convert that into a KPI? So building that in sort of at a second step. And then of course, the third column is the measurement approach, exactly the same as when we did it on the thermal part. And then one thing also when you're working with this sheet is keep in mind when you're working on the thermal part, then out on the left, or sorry, on the right, there's a lot of additional columns, and we thought about maybe hiding them and locking them, but again, then the risk of making some errors is there when you don't see them. So we're just making it open. So please keep in mind when you add in new lines, sort of copy the whole line and paste it in, because otherwise you will not get this function. And these functions we are using for in some of the result part where we are calculating how the energy is used, and we will get back to that. Yeah, Anders, I think that was all.
Yeah. I don't know if we have some questions regarding this this part, or if we should just continue.
There are questions coming in, but for now, based on the experience or interactions with the EACs or the energy auditing companies during the demo audits, I find there's a lot of confusion on this column J and K, the dry matter and the specific heat part.
Mm-hmm.
Maybe if you could elaborate again further on that, because
I think yeah, sure, Raul. And I think this is we thought about actually removing it from this sheet because it can be kind of confusing. The only reason why we decided to let it stay is just to demonstrate that sometimes if you will build in more dynamics into your model, so letting your heat capacity depend on the dry matter and the temperature, then you will get even more dynamics in. If your temperature changes when you're updating, then the specific heat will also, the heat capacity of the specific flow will also change. But otherwise, it doesn't really have a saying here. We could decide to make the heat capacity column K, a yellow column where you just punch in a fixed number and then delete column J. That could also be to avoid any confusion in the future. That could also be, it's more like for showing that if you want to build in this dependency, then this is a way of doing it. But yeah, I can see why it can, how it can be confusing what we are actually using it for. But I think you could, I mean the CP value, now there is a function for that. This is a function for a dairy product, and I think this will not work for many products. So I think just changing it, having it to a fixed value might be, yeah, avoid a lot of confusion.
So the experts or the auditors can directly add the CP value which they think is relevant for that product stream or something, right?
Exactly.
Okay.
Yeah.
And just to add another point here, some of you might be coming across some processes which have phase changes happening.
Yeah.
So that time it's like the heat of evaporation as well as the chilling. That does have to be considered. Yeah.
Yeah. What we have, I will get a bit back to that in some of the dilemma discussions, but let's take it now. If we have a phase change, for instance, then we don't have we can have a slight temperature change due to pressure, but for now we are not really considering the pressure here. So ideally we would not have a temperature change. So we only have the energy related to the phase change, and this is what we should put in as the heat capacity. So this number will be way bigger, and then we should set the temperature, because if we have the same temperature in and out, then we have an issue related to our calculation and to our way of demonstrating. So the way that we do it, then we have a 1 degree temperature difference. So going in with 100 and going out with 101 degree or whatever. So just having, or even minor, but it's just to avoid that we have a division by 0 in some of these.
So perhaps I'll just skip to this utility mapping sheet that we have here as the next one, where you have it's divided into 4 columns here. We have the purchase, the conversion, distribution, and consumption. So you should take these columns each one by one, going through it, and then in the purchase you have all your fuels coming in, or energy sources. You will have like natural gas, coal, or biomass, whatever you have as fuel sources that you purchase. That then enters the conversion part, where you have your, for example, your boilers or chiller or compressed air system. Here you can estimate the losses throughout the system, so they add up. You have energy losses that sums up, which will of course not be available for the energy balances. Then we have our distribution systems, steam distribution, hot water, compressed air systems, or glycol, whatever you have on site. That could also be the distribution losses throughout the process. And then at the end, we have the consumption, which is the heat available for the processes. And that then here adds up the different energy available for the process. We can see we have a mapping to E here that kind of shows how much of the energy that is coming in is also coming out towards the end. How much do we do? How much of the energy is shown here and not in the energy balance section. I don't know if I missed anything here, Fridolin, but
just a few comments. Again, here you can see sort of the yellow parts are the ones that you can fill out. The blue ones are input from other sheet. So this is the natural gas coming in. And in this example, we are using natural gas on 2 boilers. Then we have a split. We don't have a meter on each of them. If we had, we could just divert it directly. But here we have a split saying, is it 80, 50, 85, 15, something like that?
Yeah, 92 and 8%.
Okay, okay. So a large part goes to boiler 1, and then we have a minor part going to a hot water boiler. And this is just splitting out the natural gas consumption between 2 boilers. And then, of course, the losses, as Anna said, you can put in if you have a total loss. And here we just make some example of how what are the different loss elements. We have some losses, and you can always discuss whether it's losses or it's a consumption. But in this case, it's an energy that is consumed or removed from the energy balance. Okay, can you go back, Anders?
Yeah, sure.
From the energy balance, and we have said, okay, in this case, you could consider what is the consumption related to blowdown, because this is something that will not end up in the process. We have a deaerator, we have flue gas, and we have radiation losses. There could be other losses, but here you can put them in. You could also, if you have an overall efficiency of your boiler, taking the different elements into account, you could just put it in as the total. And that will sort of subtract, because you can you make it a bit bigger, Anders? I can have a hard time reading. Yeah, good. Here you can see you have 18 million kilowatt hours going in of fuel. You have a loss of 1.8, so 10%. That we have to subtract. So we have the remaining part is being converted into steam. And now we have a number saying 32 million. This is higher. And this is because we have another steam boiler that is based on coal. And that also contributes to a part of this consumption. So the sum of these two adds up to these 32. Then we are looking at our steam distribution system. And here we also know that we have some losses related to the steam distribution system. And these losses are extremely difficult to estimate. How high are these losses? Because there's a lot of factors that has an influence on this number. We have several times tried to model the losses of these steam systems, and every time it ended up being very big and very complex models. And we ended up by making a lot of assumptions related to the state of the insulation material, the extent of the systems, and so on and so forth. So this will be associated with a lot of uncertainties, even though we make a very sophisticated model. So for now, we will just make a rough estimate based on the state of the distribution system. If it's very new, is very well maintained and insulated, this number will be very low. If it's old, poorly maintained, and also very widespread, a big system, then this number will be higher. But it is extremely difficult to put in a number here. You could maybe, what we have done sometimes, are just calculating the losses are associated, let's say, with 100 meters of pipe. And then using this scaling up, estimating roughly how many meters of pipe, that will give you a fairly value to put in. So you can use that to justify your figure putting in here. Anyway, here we said certain percent is lost. Here it will account for 2 point something million kilowatt hours. This is subtracted for the 30 million kilowatt hours, ending up around 30 million kilowatt hours. That is being fed in to the process as an energy consumption, supporting the energy service that we have been mapping in the process mapping. So this figure saying here 27 million, that's a figure from the process mapping. So that's the sum of all our calculated consumption related to the specific processes. And then we combine or compare this figure to what is actually supplied by the distribution system. So what ended up in the process. And here we can see we have a deficit of 2.9 million kilowatt hours that is not mapped, and that is equal. And then we have this term mapping degrees, 92% mapping degrees. So here we cannot account for 8% of the energy consumption. We cannot account for it. And that could be due to many issues. It could be losses internal in the process that we are not accounting for. Maybe we've overlooked some processes. It could be the distribution losses, it could be losses related to the conversion. But we need to look at this figure and say, can we accept that we cannot account for 8%? Is it relevant for the stage that we are in now? Do we have better intelligence, or should we start working with the energy mapping as it is, start developing project, estimate the magnitude of the project, and then decide whether we should try to improve the mapping degree if it adds value to our project development? And if you go down a bit, Anders, and then to left, yeah. Here we have some other systems, and we have the electricity. We know how much electricity we have bought or generated. We have some chillers, we have some compressed air, and then we have some electricity users. The chillers, in this case, we have estimated, calculated, measured, whatever, an energy consumption of 7 million kilowatt hours. This is what we are using on the chillers. Then we know that the coefficient of the performance of our chillers is 3.5. This is a value that we have got. Maybe it's been a measured value. We have got it from the supplier. Maybe we've retrieved that in other ways. And using this value, we know how much energy that is actually converted from electricity until our cooling system. So how much cooling are we generating that is supporting the process? And we do the exact same exercise. So now we know how much cooling that is being generated by the cooling system. We have some losses related to distribution. And then we can compare to the cooling demand from the process. And we again have a mapping degree here, as we had with the thermal system. Then we can look at the air compressor. In this case, in this example, we have an air compressor. And as you know, that air compressor is a relatively bad energy carrier because we put a lot of energy into it. And most of this energy is converted into heat. And some is, of course, converted into electricity. But in this case, we have a recovery system. That could also be a recovery system on the chiller or other utility system where we have a recovery system. And what we are illustrating here is that here we are recovering 80% of the electricity that is being used on the air compressor, that we are recovering, and we are putting it into the hot water system. So this recovery system works in parallel with the hot water boiler, adding up to the hot water process. And we do exactly the same with the hot water process. We look at the mapping, what we have specified that we're using, and we look at the mapping degree again. So it's similar. And the remaining electricity in here, we have specified 2 major electricity users in the utility system. It could also be the boilers, could be added or whatever, some other. And then the remaining part goes to the production. And again, then is compared to our mapping of electricity in the production. And we have a mapping degree here, also saying how much are we accounting for here. Okay, I think that was it.
Yeah, but just a comment, as you said, it's very difficult to estimate these distribution losses, and you shouldn't try to gain 100% mapping degree just by adjusting the distribution losses. So in order to fit the energy balances here and also the utility, but try to get as close as possible to whatever is right in reality. Yeah, then we go to the second last sheet here, which is the supporting system. And that is a kind of the systems that doesn't really fit into the conventional mass flow balance and process mapping. So for example, we could have a cleaning system or a washer, or if you have a packaging department, so you can kind of model or make your own very simple schematic diagrams equal to whatever you saw in the energy balance. And this is then, it's important that you can then convert this into this sheet. So it's not automatically converting or supplying the data you enter here into the process mapping sheet, but you have to do that yourself in order to account for all the different parts of the site. So basically, this is just for any unconventional processes that you might have. So
any process that is not done, or any consumption that is not directly linked to the production. So as Anders mentioned, it could be, for instance, all the cleaning systems that you have, could be some transport issues. And here, this is like a sheet where you are sort of more free to calculate. It could be often what we, for instance, if we do a cleaning, what information do we have related to cleaning? Maybe we use some assets, we use some live. So it could be different kind of additive where we actually have some numbers. And then based on that, and we also know how it should be diluted into water, we could make a calculation of how much mass is used to calculate, or to that should be heated up for these cleaning. So there could be many ways of retrieving this information. And then, as Anders mentioned, it's important to convert that into so to energy and to temperature. So we get these sort of two elements into our process mapping, because that will be, then this will be displayed in the result part correctly. So yes.
And perhaps we should just jump into the results. This is the first sheet that you meet when opening the energy mapping, and it's important because here all the results are displayed. It is displayed in overall heating of steam, overall hot water. Then we have different cooling systems or distribution systems that we have. We have the waste stream sources and electricity. You should, of course, customize this to whatever fits the site the best. So whatever systems they might have, and if it makes sense just to like combine hot water and steam, if you have a overall heating display instead of separating. But generally, it gains more information if you try to separate it into as many different distribution systems as possible. But yes, here all the results from the other sheets are accumulated or ends up. You can see the part of the losses, the not mapped, and then you have the total. You then see the mapping degree once again. You have to ask yourself, are you happy with the mapping degree? Is it sufficient, or do we have to go back into the mass balance or the energy balance to kind of look if there was an error, if we only get a mapping degree of 60%, something like that, or we get 120% mapping degree. In the bottom here, we have some different charts. Here displays the accumulated consumption of heating and cooling with the temperature on the x-axis here. And we can go into this graph, go into 80 degrees Celsius and seeing, wow, we're actually using 80% of all energy on site below 80 degrees. That might refer to, do we have, are we using steam for processes that is not requiring steam? So could we use hot water instead, or could we implement a heat pump, or making any energy saving projects? And we also have these two, which are overlapping the cooling energy consumption and by temperature, and the heating energy consumption by temperature. And we can see this grayish area that is overlapping is the part where we could actually make direct heat recovery or integration of heat exchange. And the yellow one we have here is available waste heat that we entered in the process mapping here. That can then be used directly for heating of any processes throughout the site. And of course, you should take these results and analyze them yourself. Find out what is it that we in the beginning stated that we wanted to use the energy mapping for. Is it economic evaluation of emissions, or is it to make energy saving projects? Yeah, Ferlin, do you have anything to add to the results section, or should we move on?
Just a few words. When you look at the results, then of course you can again we display the mapping degree, and if you go down on the temperature analysis, then these are more to get started, to get inspiration, and also seeing and starting up discussions, because these are very ideal situations. So saying, okay, for instance, this figure shows, as Arnaud explained, that 80% of our temperature of our heating demand is below 80 degrees. So now we could start up discussing, okay, why have we designed our energy system the way that we have? I mean, 80 degrees is very suitable for heat recovery systems in many different ways. It could be direct heat exchange. It could be by a different kind of booster system like heat pumps, other systems. Another thing we could see here is also that when we go in and look at the cooling curve, then we could see that if we go in at 20 degrees, we are only covering 7%, something like that, maybe 10, 15% of our cooling demand. And if we have conventional cooling system covering this cooling demand, we should, chillers, for instance, so we should consider, could this be done in a different way? Could it be done more efficient? But now it becomes relatively visual to see what is our process actually requiring. And we have seen several examples of companies achieving significant savings in start tailor-making their energy systems to the process demand or the energy service, instead of having one system fits all, because that is often relatively inefficient way. And if we take the temperature analysis in the bottom, this again is an ideal situation where you can say, okay, if we could recover this whole cooling demand part, we could put it into the heating, because we have a temperature match, we have an energy match, but we all know that in order to transfer energy, we need a temperature difference. We have some losses on the way, so these might be put a bit apart. But again, then these are good illustration to start reflecting on some of these potential, and also the waste heat stream available. Why do we not utilize that in some way to covering some of our low temperature heat demand? So putting all these into the equation.
These are just slides representing all the sheets that we have been through. So the results section and the energy heat recovery. In order to conclude on the energy mapping, we then gain a further detail each year based on the previous mapping that we did. So that is the overall goal of the energy mapping, in order to increase detail and the knowledge that we gain from this. You can use that knowledge for energy saving projects, emissions and environmental impact, gaining a better process overview. So combining all the different departments into one sheet, getting this mutual understanding of how does this factory actually work. You also get to locate how the individual fuel type is used throughout the facilities. And then you get the overview of your heat energy losses or distribution losses throughout your system, and you have your heating and cooling requirements at the individual production lines or even individual streams.
Here, just some. We will not spend too much time on it. It's just to show that we have been using this approach, even though it's relatively simple, but it's actually been the basis for a number of very, very large projects, both in Denmark and internationally. Here's some example of a food ingredients company that actually want to become carbon neutral by electrifying. And the basis for all the decisions in terms of converting from being a fossil-based production to a 100% electrical-based production was the energy mapping. And the end goal was that we could retrieve actually a carbon neutral production, and we will at the same time save 70% of the energy consumption by applying different heat recovery methodologies, both directly and indirectly at the production facilities. Again, another example of where the energy mapping we used was in a brewery, where we mapped the energy consumption, and based on that, it suddenly became very visible where we could find potential for. They have a very widespread recovery system already, but there was potential for actually improving the existing heat recovery system significantly. So we could actually reduce the energy consumption by 30% by applying some more process integration, also based on the energy mapping. So to go to the next slide. Yeah, just two more examples. Again, then two dairy examples. One is where we looked at the cooling systems. We have mapped it, the cooling system. We know how much surplus heat was available. We applied a heat pump and then made a 90-degree hot water system. And that could actually both serve for as cooling, covering the cooling demand, and then also the whole energy demand below 90 degrees. And here we also used the temperature curve, challenging the way. This was based on steam. They had 8 bar steam before we started, and now we could see that a large percent of the demand were below 90 degrees, so we could easily cover this by a 90-degree hot water system that could be made by a heat pump, both covering cooling demand and this low temperature heating demand. And then the last example is also again where we could match. We have the different processes. We have some heat recovery potential from the air compressors, from the cooling systems, also from some flue gases. And we merged that into a recovery system, and we could actually cover a lot again of the low temperature heat demand. So putting this into actually, in this case, an existing low temperature system, just leaving out the fossil demand. Yes. Yeah. Then when looking at, there's a lot of dilemmas, and I think we have talked about most of them already, but I will again then just highlight some of these dilemmas, because I mean, this tool is not a perfect tool that can cover everything. You cannot just take a component, drag and drop, connect it. This tool, and it's the purpose of this tool, is that it is a simple tool, simple working tool, and it can be used by anyone. It can be shared by the companies. Almost everyone has an Excel tool, so it can be shared. It can be looked at together with companies, because there is a lot of commercial available tools that are very sophisticated, very precise, but you need to use these tools on a daily basis. You need to be an expert in this tool. It's hard to share with your customer, also for the customer to have the tool and maybe use it as their daily work with their daily energy management system. So having such a simple tool also compromises some of the the way that we are actually mapping, and this is also where it might be a bit more sort of handhold some of this mapping part. For instance, when we have the drying process, how do we map a dryer? If we look at it from a process perspective, I mean, we could say that we have a certain amount of product going in. We know how much water should be evaporated, removed, but often these dryers are associated with a number of other elements that contribute to the energy consumption, and that we do not sort of catch in that. We could go, if we can get a KPI from the supplier, that could be one way. Or we could actually, if we have a value on the air, because often in a drying process, you heat up some air, and then you merge the air with your product, and then the drying starts taking place. And often you actually, maybe you have a meter on the airflow instead. So sort of look at it from an air perspective, and then you have your airflow and you know how much you need to heat up your air. Then you actually get a relatively precise view of how you are using, how much energy is used for that specific process. And then you can always generate a KPI and relate it back to the process afterwards if you want that dynamic effect built into it. The same goes for evaporators, and we have talked about evaporation, condensation. These phase changes in general, they can be tricky, but it's just the energy used for the phase change should be put into where you have the CP value, and then using a temperature different of 1 degree, then you will be good for that one. Then Anders has also explained there are sort of unconventional systems, like the system that is not directly related to the process, and they need to be dealt with in this sheet called supporting systems. And here you are sort of more free to set up any calculation that support, as long as you can just, by the end of the calculation, refer it back into the process sheet. Then, of course, we have the issue of mixing the streams. We have, how do we find the CP value of mixing streams? I mean, you could have an average weighted CP for the streams, or maybe you could find a CP value for this mixing product as an alternative. There's also exothermal and endothermal sort of energy that is being generated or being used as a part of the process. And this is also something that needs to be based on a KPI approach or measurement, because it's hard to fit it in, because it's not related to the temperature difference only, because a chemical process or reaction is taking place. We have been talking about the dynamic of the model. Try to build it as dynamic as possible, in the sense that you should minimize all the different elements that you should keep updated, so it becomes easy to update. Also because we have seen that a lot of companies, they also use this simple energy mapping just for making predictions, saying next year we know that we assume that this is how our production will look like. How will our energy costs look like, or our carbon footprint look like for next year? And then it's, of course, nice if you don't have to go in and update and take a lot of measurements and everything to just get this rough estimate for the budgeting part. Then there's the utilization of surplus heat. We had the example of a heat from the air compressor. But as a rule of thumb, if the utilization of the heat is done within the production, it should be treated as in the process sheet. If the heat source for the utilization of the surplus heat is emerging from the process, then you should treat it in the process. But if it originates from the utility systems, as we showed for the air compressors, then you should deal with it in the utility part. This is just a rule of thumb that we're using when we are working with this heat recovery system. And of course, they can go across the line. So utilizing something from the utility system, putting it directly into the process. And then this should just be illustrated by an arrow going into the process and relate that to the process figure, as we have done with all the other different kind of systems. Then there's the whole question about when do we have a sufficient mapping degree? And it's very hard to say precisely, but often when we do the first mapping, then we are saying if we are within 85 to 90% mapping degree, we are good. If we are below, then we need to do some reconsideration if we have overlooked something, or need to reevaluate all our assumptions and see whether this should be, if there's any errors or we have overlooked something, to increase the mapping degree. But when we are, let's say, at a mapping degree of 90%, this is good as a first approach. You can start developing projects, identify projects, and then when you have developed the project, then you can decide whether a increased mapping degrees has a positive effect on your specific projects when you are developing them. We have talked about the thermal losses. It's very hard to quantify. You could come up with some, by experience, a figure, or you could make some calculation. Let's say if you have a system, you have an estimated saying this consists of that many meters of pipes. You can make a calculation of 1 meter, so a pipe equivalent, and then scale it up. Then you get the magnitude. So you can justify how to have I reach at 3.5%. This is the approach because I don't have any better intelligence, so I've used this approach. Then there's the last one I've put up here is the mapping of the compressed air. The amount of air, we have put it in the example, but often the amount of air is not that interesting in related to the energy mapping. However, when this is said, I think when you are scouting, when you're doing your energy screening, you should evaluate your processes, whether they are using compressed air or not, because as explained earlier, then an air compressor is an extremely inefficient energy carrier. So could you sort of, if it's just a matter of, we had an example on a textile factory where a sewing machine were operated on compressed air. And there could be a number of good arguments why it should be operated on compressed air due to some process technologies. But if it's just a matter of operating it, having some energy converted, and this is operated, then it's very inefficient. And you should definitely look at what would the total cost of the ownership of this sewing machine be using compressed air. And I think then you will discover relatively fast that by converting this into electricity direct driven, it will be a payback that is relatively low. We have some examples, last example here of sort of the process of developing a project based on the energy mapping. I will go through it very fast. This is just saying, okay, here we have a system. We have mapped it out. We have identified that we have a surplus heat from cooling of evaporators. This surplus heat, we can retrieve it, put it into a heat pump, and put it into a hot water system of 85 degrees. So this is what we actually discovered based on the energy mapping such a system, and so this is the first step. Then we start, if you go to the next slide, Anders, then we start developing the project. And we use the energy mapping for the basis for the tender, saying how much energy is available, what are the conditions for the energy that is available. And so this was also used for the basis for the tendering material. Then when we got back the offers from the tenders, then we could also use to evaluate the different offers. So the efficiency of the proposed system, so on and so forth, will also be used as a part of we use the energy mapping to evaluate the system. What are the consequences of using these different offers that is proposed into this system? Does it conflict? Do we have sufficient capacities? So on and so forth. And then finally, when we have built the system, and then it should of course be integrated into the energy mapping. So the energy mapping again then reflects the new situation on site. So this was just to show that how the energy mapping is a part of such a project, both the initial phase, the whole design, tendering, and implementation, and finally updating it to the new situation. And I think that's all that we had on the program.